because one of the things I said you didn't need to worry about was determining oxidation states and all those oxidation numbers. There is a question in the sapling homework looking at oxidation states and oxidation numbers. So theoretically, this is all review, but let's check. How do we determine those oxidation numbers for, and I'll interchange between numbers and states, because they're ultimately the same thing, just depending on who wants to reference it. How do we determine those oxidation numbers for iodine, oxygen, and carbon?
Look at their formal charges.
It is not technically formal charge, so we have to be careful. Formal charge and oxidation state are two entirely different things. Formal charge is something that's associated with a molecule. Okay, oxidation state is associated with an atom. Okay, very different things. Okay, they are related. For instance, if I gave you the quote-unquote molecule of copper plus 2, what's its charge? Plus 2.
Which means it lost 2 electrons.
And its oxidation number is still plus 2. Okay. So they are related to each other, and that's where the confusion comes in. You look at, well, it's the same thing. It's not the same thing technically. It's how you get one from the other. The charge comes from the oxidation states. Okay. So what we end up doing, and that comes from, I need to get some space, so I'm going to erase the copper plus 2 there. Just put it over the top. Is that we look at an individual molecule, and we look at the number of a particular atom, and we multiply it by its oxidation number. And we go, that is writing, right? Yeah. And we look at the number of the next atom. So how many of them are there? Times the oxidation number of that atom. Okay, and we do this all the way out for the entire formula. Once we've got the entire formula and we sum all of those values, what does that end up equaling? The overall charge on that molecule. Okay. Hence the parallel. If we now look at our formula for our copper plus 2, how many coppers are there in that formula of copper plus 2? How many coppers? Just one. What's the oxidation number? Plus 2. Okay. If you aren't sure what the oxidation number is, that's fine, because technically it is something you have to solve for, so we can put X. Okay. What's the next atom in copper plus 2? There isn't one, so that has to then equal what? The overall charge, and the overall charge is plus 2. How do we know the overall charge? The overall charge is always given to you. The overall charge is written in the upper right-hand corner. The oxidation number is rarely given to you. It's something that you technically should be calculating every single time. But there are certain cases, like here, what is X for my oxidation number? Plus 2, because that's what happens when I solve that equation. It equals plus 2. Okay? So it's coming from that equation, and that's the relationship between your oxidation number and your overall charge. Overall charge applies to the unit, whatever that unit may be. The oxidation number applies to the atom, specifically the atom. When we're looking at an ionic compound, I'm not sure I wanted to erase all that, but I just did. Okay. We could now shift up to, say, pick an easier example, I2. How many iodine atoms are in I2? 2. What's the oxidation number? Officially, it's something we have to solve for. What's the next atom? In I2? Nothing. What does that have to equal? That has to equal the overall charge. What is the overall charge on I2?
0.
0, which is written in the upper right-hand corner. Okay. Nothing is written there, so it's 0. What is the oxidation number for iodine in I2?
0.
0. Okay? So if you think back to, it's probably 152 when you saw this. Okay? They reference the oxidation numbers, and there's things that you had to memorize. And one of the things that's usually on that list is elements in their elemental state have a 0 oxidation number. You don't have to memorize that. Understand where oxidation number is coming from. It's the balance of the oxidation numbers relative to the charge. If we have any element in its elemental state, its charge will be 0. Well, if its charge is 0, the oxidation number will have to be 0. Okay, so it's not something that's this big extra thing to memorize. It is coming out of the definition of what an oxidation number is and what charge is. Okay. Now that I erased that, was there a question on I2? Okay. Are they all that straightforward?
No.
Okay. So let's pick something else. Which one do you want to pick? I205. Okay. How many iodines are there? What's the oxidation number of iodine?
The overall charge.
The oxidation number is something that you have to solve for. Okay, so it's X. Is there something else in that formula? How many oxygens are there? What's the oxidation number of oxygen? Okay, so I'll accept you don't know. It's not X. We have to use a different variable, because if it was X, you're saying it's the same as iodine, and that's not necessarily true. This has to equal our overall charge, which is, how do you know it's 0? Nothing in the upper right-hand corner. Okay. So now what happens? We got 2 variables and 1 equation. Can you solve that? No. Okay. So we've got an issue here. This issue is resolved by one of the couple things that you were supposed to memorize when it came to determining oxidation states. What was that one of those rules?
Oxygen always has a -2.
Oxygen has a -2 oxidation number every time, with one exception, which we won't see, but what's the exception?
What is attached?
Peroxide, H2O2. Okay. In those cases, the oxidation number becomes -1. Okay. Super, super, super rare. Okay. So anytime you see oxygen, you're seeing an oxidation state of -2. What does that help us out with? We now have 2 equations and 2 unknowns. Y happens to be -2.
What were the other rules?
I only remember some of them,
It's in the
to be
book.
honest. It's not in your textbook. The reason why it's not in your textbook, it's Gen Chem 152. Yeah. One of the ones is hydrogen is most commonly a positive. Metals. Metals will always equal their standard charge. Okay. And then I think halogens equal -1 as long as they're not bonded to oxygen. Okay.
What if you're dealing with chromium? How do you determine whether it's like +2 or +?
So it's the metals that have standard charges.
Oh, okay.
So all of your group 1 metals only have 1 charge. So their oxidation number will be, for the group 1 metals,
+1.
+1. The group 2 metals,
+2.
+2.
Oh, okay.
So there are certain metals that have a standard charge. Their charge is the oxidation number, because there is only one way to balance out the electrons and protons. There are other elements that you have to calculate the oxidation number for. That's because they have uncommon charges or different charges. Chromium's one of them. Iron's another one.
Aluminum,
Aluminum's a +3.
always?
Yeah.
Is it a +2?
No, it's a +3.
It's in the third group.
It's not just because it's in the third group. You got to be careful with that. But aluminum is considered a +3.
As far as the loss of electrons when that occurs, those oxidations for those types of metals,
Mm-hmm.
those electrons are given away from the highest orbital?
Those are going to be your highest orbitals because we want to remove electrons from our highest energy so that the overall molecule gets lower in energy. If we removed electrons from our lowest energy situation, we're only making our atom higher in energy, and that's not a very standard thing to do. Okay. Really the only rule that you're going to need to focus on, and I think even for the homework question would be oxygen's going to have an oxidation state of -2, and then you're also looking at this formula. Okay. The relationship between your oxidation number and your charge. Okay. So if you're given a reaction, theoretically you should go through and check to see if the oxidation numbers have changed. Right? And you should check every single atom. Okay? You could see how this could get a bit tedious for, say, biochem, because I'm going to jump ahead a couple times. We're looking at a structure for NADH, a relatively small molecule as far as biochemistry is concerned. How many different atoms do we have? A lot. Okay? So going through and calculating all the way through that is going to be a bit tedious. Okay? So we'll come up with other ways that we can address that. Okay? But the reason why that sapling question is there is to make sure that you understand the fundamentals of how we go through it and pick out those oxidation numbers, and we try and come up with simplifications when we move into biochem. Okay? And ultimately those simplifications are also following from OChem. Okay? So OChem simplifies it down a little bit for us, and then biochem we take it a step further. Okay? So that gets us to our oxidation numbers for each element on the reactant side, for each element on the product side. Okay? And one of the approximations we make in Gen Chem is that every element within that structure has the same oxidation number. So please feel free to go through and test that theory for any of the structures that we're dealing with in biochem. It's not true. Okay? Nearly every atom within, or type of carbon within an individual structure in biochem has a different oxidation number. Okay? So depending on what we're looking at, we're going to be seeing different things. Gen Chem, our molecules are really, really simple, so we don't stress as much about it. Okay? The next part is we would then compare reactants to products for an individual element and see what happened to it. We went from a +5 to a 0, or I did what to the number? I decreased it, also known as reducing it. Okay? So if we decrease the oxidation number or reduce the oxidation number, we've done gained electrons, and that type of reaction is reduction, hence the reduce. Right? That's where that reducing came from. Or sorry, not the reducing, ignore the ing. If we take a look at the oxygen didn't change its oxidation state, so we don't care about it if we're looking for redox reactions. For our carbon, we went from a +2 to a +4. Okay. So to do that, we increased our oxidation number. Okay. So if we increase our oxidation number, we're doing an oxidation, and to do that, we have to lose electrons. Okay. So there's now these parallels between them. One of the approximations that we talked about, and before we even do that, however you remember the parallel between loss of electrons is oxidation and gain of electrons is reduction is fine. I don't care how you do that as long as you remember it. Okay. There's a variety of ways to do it. Like we already said, Leo says Gur is my favorite one. Okay, that one just sticks. The other thing that we said we got to watch out for is anytime you see ing, you should really slow down. Okay. We ran into this issue with the carbohydrates. Oh, we had reducing sugars. Okay, well, what did that mean? They caused something else to be reduced. What happened to the sugar? The sugar was oxidized. Okay, so as soon as you see that ing, you got to be careful to make sure you know exactly what's happening within it. Okay, so that you're classifying that appropriately. Okay? When we got to oxidation and reduction in organic chemistry, our molecules step up in difficulty, which makes it a little more challenging to determine our oxidation states. Okay? So one thing we could go through and do is look at what things are attached to it and just say in general what's happening. So the reason we use the term oxidation was ultimately because we watched our reaction react with oxygen. The more it reacted with oxygen, the more it was oxidized because there was more oxygen present. That's the term oxidation, where it's ultimately coming from. So if we look at our structures, particularly our carbon structures, because this is a derivative of organic chemistry, if we increase the number of oxygen bonds, we've increased the oxidation number. Okay? Knowing specifically what that number is becomes a little bit more challenging. You are responsible for that. There is a question in the homework on it. If we tried to go through and do the method that we just talked about, sorry, I thought it was this slide, doing all the charge and the balance and all that fun stuff, okay, for a relatively simple structure that may not be too bad, but it's probably a lot more work than you really wanted to go through and do. So we want some other way to evaluate that. Okay? This is where I messed up on the definition of homo and heterolytic, and I always get it backwards. Is this actually working? Okay, good. So we'll look at an example of what homo and heterolytic mean. Okay. In a homolytic situation, what we are referencing is the electrons in that bond going back to their part or original atom. So we can use a fishhook arrow signifying that one electron in the bond went back to A, one electron went to B. That is a homolytic bond cleavage. Okay. If you go through and count out a bunch of homolytic bond cleavages for all your individual structures, you'll find that you're pretty much getting darn close to a valence electron count. Okay. It's a little bit off with charged structures, like positively charged carbons. It's not officially the valence count. You still have to go through according to this homolytic. But for most problems, you'll be okay with thinking about the valence electrons for an individual atom. The heterolytic means what? Both electrons go to one atom. Well, which atom are they going to go to? They're going to go to the more electronegative one. So in this case, I'm saying B is more electronegative. Okay. So let's take a look at determining some oxidation numbers to make sure. Let's take a look at the carbon and CO2. Since we don't have any charges, we don't have to stress about that valence versus homolytic, and we could just jump to our valence. So it's got 4 valence electrons. Officially, what we would do is break each of those bonds homolytically, having problems drawing single-headed arrows. Okay, and we would see in the middle there we have 1, 2, 3, 4 electrons on our carbon. Okay. And as I think about this more, that valence thing really only works for carbon, unfortunately. Okay. Then what we have to do is subtract by the heterolytic bond cleavage. So we now go back to our structure and say, okay, where would I expect these 2 electrons to go? To the oxygen. Whoops, double-headed arrow. How about the next 2 pair of electrons? And the next? Which means carbon has a total of 0 electrons. The oxidation number then for carbon becomes +4. Okay, because 4 minus 0 is 4. It's usually a good idea when we're referencing our oxidation numbers to specify that positive or negative. So you'll always see me include that positive to really accent the fact that I'm looking at a positive value. Okay.
So you can, there's 2 ways to find the oxidation? Because we did the other one where it was like times the oxidation state, and then you could do 4 minus 0?
So if you went through and did the oxidation state calculation, it does work for a molecule that's this simple. Okay. For CO2, it works very well. As we move up to something like this, or something like this, or worst case scenario, something like this, okay, we don't want to be using that other method. Okay, it's going to be way too advanced. Okay, it's going to be beyond the scope of what we really want to work with. Okay, so it's not that it doesn't work, it's that it's a lot more work than you want to go through and do.
Yeah. So where did the 4 come from?
The 4 was the homolytic bond cleavage. We look at each of those bonds and we say, if we break those homolytically, how many electrons would be sitting on the carbon? And ultimately, in this case, what we're focusing on is just the oxidation number for the carbon. Okay? I could do the same thing and calculate the oxidation number for the oxygen. Okay? And that's where this valence thing in here doesn't work very well. So the valence really only works if we're looking at carbon and uncharged carbon. Okay. What happens if we look at the very first one? Let's assume we're looking at hydrogens. Actually, let's make one of those a carbon. What's our oxidation number for our center carbon? So what do we go through and do? Break each of the bonds homolytically. How many electrons? We would have 4 electrons in our homolytic situation, okay, minus the heterolytic situation. So in our heterolytic situation, we need to break those bonds according to the electronegativities. Carbon is more electronegative than hydrogen, so it will take the 2 electrons, switch up our color, and probably draw this all the way out. Yeah, I didn't think I could gently erase that. So our carbon would take those 2 electrons, those 2, and we'd have a total of, so far, 6. What does it do with that last pair of electrons? Why is it an even distribution? You have the exact same electronegativities between carbon and carbon. So carbon really, our center carbon only picks up 1 of those. So we have a total of how many electrons? 7. Our oxidation number becomes, for some reason that looked really weird, but it's -3. Homo minus hetero. Every time.
So then you end up with less than
Okay, so you end up with a -3 on the fully reduced side, and on our fully oxidized side, we had a +4. Okay, well, if we think back to what we were talking about with our oxidation and reduction, the oxidation term doesn't really mean much, but our reduction term meant we went to smaller oxidation numbers. Okay, so as I move from CO2 all the way down to this ethane-like structure, okay, what happened to the oxidation number? It was reduced. Okay, so the smaller our oxidation number, the more reduced it is. Okay, the larger our number, the more oxidized it is. Okay, so we're looking at that balance all the way through. So in organic chem, in some cases you were asked to do it, and usually where you were asked to do it is in very particular locations. Okay, what would those very particular locations be in organic chemistry? Not just carbons. So if this was given to you in organic chem, where would you calculate your oxidation number? Said another way.
Isn't it just 0?
I see a carbon here, 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 here. Do you really want to calculate it for every single carbon?
No.
Okay, no. Okay, remember, organic chem makes some simplifications, which they've actually already kind of elucidated in the process of this problem. Do you think any of the carbons that have red dots on them now are ones you should calculate the oxidation number for? Why not? Everything's still technically happy.
They're less likely to react if you were to look at the compound
Oh,
itself.
right.
It's better than that. You're right, they are less likely to react. They're so less likely to react that did I even bother to draw out the rest of that structure?
No.
Why not? It did not react. Not less likely, period. It did not react. If it doesn't react, does it change its oxidation number? No, so we can ignore it. That's why we can ignore it. So when we're trying to determine our oxidation numbers, where we want to keep our focus located is where things changed. If something didn't change, why bother to calculate its oxidation number? It didn't change. If I calculate it once, it's still going to be the same at the end. Okay? So we can now look to see where our change occurred between these two. Okay? This is going to be a big thing that we're going to keep talking about in this class through the metabolic pathways, is look at a reaction and identify the change. Once you've got the change, you can start to come up with ways on how that change occurred, and that's going to be the important part. Okay? So where is the change? What changed?
The nitrogen and the top carbon.
Okay. Our nitrogen changed. What changed about it?
It was reduced.
Okay. We could go through and look at our oxidation numbers, but what changed to go from a positive to neutral? Gained electrons, which means it was reduced. Good job. I didn't actually see reduced. I was like, no, that's not right. This is why I look at the electrons. And remember, Leo says pure. So it gained electrons, so the nitrogen was reduced, okay, in the course of running this reaction. So what we're trying to do is just identify that change. The other thing that you mentioned was that you said just the hydrogen, or did you say the carbon too? Okay. The carbon, whoop, come back here, carbon, also changed. What changed about it? Okay. It's not so much that, oh, blue on blue, that was a horrible choice. It's not so much that it lost a bond. Okay. It gained that hydrogen. Okay. So we have to be careful again on how it changed, okay, with that situation. Okay. What happened to all the other carbons? Why did you not identify carbon 5 or carbon 6? Because didn't the double bond change?
Not a carbon.
But if you focus just on the carbon, in the reactant it has one pi bond, and in the product it has one pi bond. Okay. So we don't need to look there. We would look towards our carbons where something actually changed, and we would try and evaluate what changed in that process. Okay. So we could go through and look at our overall reaction. I actually haven't done this, so I'm interested to see what happens. If we look at our nitrogen, it was reduced, but by how much? So our nitrogen in our reactant versus our nitrogen in our product. I'm really hoping this works out nicely. Theoretically, it should. So in our reactant, what's our oxidation number for our nitrogen? So we go through and we break all of those bonds homolytically, and we'd have 4 minus the heterolytic cleavage, which makes it, we break those bonds heterolytically that are attached to the nitrogen. How many electrons would be on the nitrogen? Why 4?
There's a pi bond, so 1 and 2, and
Okay, so let me draw this bond out bigger so we can see that. It's between nitrogen and carbon. If I break that bond heterolytically, where do the electrons go? To the nitrogen, only to the nitrogen. So 2 electrons from that one. How about from this one? 2.
Oh, that's right.
The sigma bond, 2. The pi bond, okay, another 2. So how many electrons? 8. Really hoping this works. Which gives us an oxidation number of -4. If we go through and look at our oxidation number for our product for our nitrogen, what do we go through and do? What does it start with?
What do you do with the 2 electrons?
Is that a bond? No, but is it electrons that the nitrogen owns? Yeah, so those need to get counted in our total.
Individually? So 5?
Yeah. So we would have 5 electrons in the homolytic situation. Homolytic means each of those bonds goes back to the partner. Now our heterolytic,
1, 2, 4, 6, 7, 8.
and we end up with,
So it's more negative, so it's reduced.
It's less negative.
It gains electrons.
so it was reduced. Okay, so now let's go up and take a look at our carbon. Carbon in our reactant. How many electrons? Homolytic.
What carbon are you talking about?
The only carbon that changed.
4.
4. Minus the, I already forgot, heterolytic.
So it's carbon with
7. Yep.
So if they have the same electronegativity, then you just say they split evenly with
They
that,
split
or-
evenly. So our hydrogen gets both, so there's 2.
2,
Then each of those carbon-carbon bonds brings in
1,
1, 2, I don't know why I split my hand that way,
7.
3, 2, and then 1 from each of the bonds,
5.
5. And our oxidation number is -1.
So we're not looking at the neighboring, like induction effects or anything when
Nope.
we're talking about
Nope,
electronegativity?
absolutely not. You are only looking at homolytic versus heterolytic cleavage of that bond. Okay. Carbon in the product. The homolytic cleavage,
8.
we keep doing that. Homolytic means each bond
It's even.
breaks evenly. Break even first, so it needs to be 4.
So it's assume it's like the number of bonds then?
And then it goes 6.
You got to be a little bit careful with lone pairs, but yeah.
Yep.
And then in our heterolytic cleavage, what happens?
1, 2, 3, 4, 5, 6.
Everybody see the 6.
Yeah.
What's our oxidation number?
-2.
-2. What happened to the carbon?
It was
Got
reduced.
oxidized.
It went from a -1 to a -2,
Yeah,
so it was oxidized.
so lost electrons.
So it lost electrons. This is the part I was nervous about.
I feel like when it becomes more negative, it should be gaining electrons, but that's.
It was reduced to gained electron. It's got a -2 charge.
What?
Oh,
Yeah, they were both reduced.
they were both reduced. No, the first one,
It was -4 to -3.
so that one was that one was oxidized.
Yeah. It becomes less.
That was
negative.
oxidized. This one was reduced.
It becomes more negative as reduced.
Okay, and this was the part I was nervous on hoping that this count worked out, which means that another atom did change its oxidation state somewhere in there. I bet you it's the hydrogen is what's happening with that. Your hydrogen also changes its oxidation state because it came in as a -1 and it becomes a positive.
Okay. Reduction is a gain in electrons.
Gain of electrons,
Okay.
so you need to go to a smaller number. So as we move from -4 to -3, that's a bigger number.
Right. Right.
Yeah, so that one was technically oxidized. So far our balance is that nothing has really changed, okay, which is what I was afraid of happening. We also have to take into consideration the hydrogen, because the hydrogen changed. The hydrogen went from a -1 to a positive, so it ends up losing 2 electrons. Okay. So the carbon cancels out our nitrogen. The hydrogen is what brings in our 2 electrons. That's not nitrogen. What's that atom? Hydrogen. Our hydrogen brings in the 2 electrons. Okay. So if we take a look at what changed to the hydrogen, let's evaluate that really quickly. It started as H-. So as a reactant, the electrons it brings in is 2, minus how many bonds does it have? 0, its charge is +2, or its oxidation is +2. Hydrogen, and I keep writing nitrogen, hydrogen product, okay? How many electrons are associated with that hydrogen in the product? Okay, we've got 1 minus 2, because of the homolytic cleavage, heterolytic cleavage, and we get -1. So we went from a +2 to a -1.
Which hydrogen?
Which hydrogen was involved in the reaction? That's the hydrogen that changed. Okay? So what we're looking at is all of the oxidations do that. So theoretically, we could go through and calculate all of that out, okay, and see all those changes. the other thing that we could go through and do as a cheat, which is ultimately what we're trying to do with this, is come up with some easier way. We went from NAD plus to NADH. What happened to the NAD plus? It gained electrons, which means it was reduced. Okay? So we can evaluate all of the oxidation states. And as we can already see, that starts to snowball and get really obnoxious to tally everything. Okay? Or we can go through and just look at those raw definition changes. What happened? NAD plus gained electrons. So it was reduced. Okay? Questions on that? So within this structure, what we need to focus on is, again, where things changed and how they changed. Okay? So if we tried to add arrows, curved arrows to show the motion of electrons, okay, we're bringing in H minus. Where does that H minus form a bond? To that carbon. Okay, so let's show the electrons coming from that hydride and going towards that carbon. How many bonds would that carbon now have? 5. Can it have 5 bonds? No. So what happens? We break the weakest bond. Our weakest bond in this case is the pi bond. Where do we move those electrons of the pi bond? Okay. We've got 2 options. We could go to the carbon. Okay. Perfectly valid move, but then that carbon becomes negatively charged because it's just gained a pair of electrons, which isn't a particularly stable thing to happen. So what does it do? It shuttles those electrons to that bond. But now what's the issue with this carbon? Too many bonds. So what happens? It shifts the electrons in that pi bond to the nitrogen. Why does that help us out? What happened to the charge on the nitrogen? Becomes neutral. Okay. NAD plus is a pretty awesome structure because it's starting in a relatively high energy state because of that positive. It wants to accept electrons to make that nitrogen happy, to make it neutral. That facilitates this reaction and allows this reaction to happen a little bit smoother and a little bit easier. Okay. What's nice about this is it is reversible. That nitrogen can just as easily donate its electrons back into the ring. But then we have too many pi bonds. So we can shift that. But then we have too many bonds in that carbon. What do we have to do?
Get rid of a hydrogen.
We have to get rid of, careful, not a hydrogen, a hydride. But hydride, yep, it's a hydrogen with a negative charge, is incredibly unstable. So it's not, doesn't get kicked off just immediately on its own to float off in solution. It has to get kicked off to react with something else. So what we end up doing is transferring that hydride, that reducing ability, okay, to our NADH, that it can then shuttle that hydrogen to another structure, okay, at a later date when it's put in the proper enzyme configuration. Okay. So NAD plus and NADH act as an electron pair shuttle. We can shuttle those electrons from one location to another. What's one of those locations? Anybody kind of recognize what might be happening in this case? It's the reduction of you usually find it after the exam. Alcohol. This is the reduction of ethanol. Okay, so what's happening in the reduction of our oxidation of our alcohol? Okay, we need to convert that into something that we can excrete from the body. To go through and do that oxidation reaction, okay, we need to ditch 2 electrons. Where can we ditch those 2 electrons? Well, electrons are incredibly unstable, which means we can't ditch them unless we've got some place to put them. What ends up happening? We can couple that reaction with the reaction of NAD plus over into NADH. How? What did we say NADH needed to react with? Sorry, NAD plus. I keep saying NADH. What changes as we go from NAD plus to NADH? Not just a gain of electrons, but also a gain of a hydrogen, so we're gaining hydride. Where is that hydride?
That's at the very top of the, was it pyrimidine ring?
So it needs to come in and attack at that position. Absolutely right. Where is it coming from?
Obviously from that alcohol reaction, not.
What we're looking at is that reaction above. We're coupling these two reactions so that they can occur. Okay? NAD plus to NADH, to get that to occur, we're adding, for all intents and purposes, 2 electrons. Okay? This is a half reaction. NAD plus to NADH is a half reaction. Okay? It's, I was getting backwards. Gaining electrons, reduction. Reduction cannot happen on its own. It must be coupled with something else. What's it getting coupled with in this case? If this is a reduction,
Oxidation.
it needs to be coupled with an oxidation. What reaction is being shown above?
An oxidation.
How do you know it's an oxidation?
Because we forming a pi bond with the oxygen, which is making double
Ish.
2 oxygens.
There it is. We have our carbon in our product with 2 bonds to oxygen versus our carbon in our reactant with 1 bond to oxygen. What did we do? We increased the number of oxygen bonds. We have oxidation reaction. Could we go through and calculate the oxidation states? Absolutely. Have fun with that. I don't want to do it anymore. Okay? Look for that changing of oxygen bonds. If I know NAD plus going to NADH is a reduction, I can now do an oxidation coupled with it. Depending on what oxidation I want to go through and do, I will couple different things. But here's what I'm going to couple here. So now the question is, I need that H minus to come in. Where is that H minus? Okay, go ahead.
Okay, so can hydride be written as a hydrogen with an electron? Is it the same thing as a hydride?
Wait, did you just say,
Like,
is hydride the same as a hydride?
Well, like a hydrogen with 1 electron, is it the same thing as a hydride?
No.
Like a negative?
Hydride, or a hydrogen with 1 electron is a hydrogen atom. It is not hydride.
It's not a hydride.
Yeah.
Okay.
Hydrogen with 1 electron is 0 formal charge.
Okay.
Hydride has a -1 formal charge. It's gained an electron. It has to be the pair of electrons.
Okay.
So where is that hydride coming from?
Has to get kicked off from the ring, right?
It can't get kicked off from the ring. It's coming in to attack the ring.
We came from alcohol.
It's got to come from this structure. Where in this structure?
Alcohol?
On the alcohol portion, functional group.
Right. Out here. Is that the answer we're going with?
Yeah.
Well, it came both hydrogens.
So both hydrogens are removed, which is the tricky part, and let's address that now. Can it be one of these hydrogens? No, why not? It did not change. Can it be the top hydrogen? No, because in our drawing, it did not change. What hydrogens changed? Okay, we're looking at this hydrogen or this hydrogen. So what we're trying to decide is, of those 2 hydrogens, which one is the most likely to take the electrons to share with the hydride? Or sorry, share with our NAD+. plus.
One off to carbon.
Carbon.
Can't change your answer now.
You're saying it
Okay.
takes electrons, so.
A lot of people said that we want to pull it from the oxygen. That hydrogen did change, but now the question is, how did it change? If you're saying that is our hydride, what did that hydrogen do to the bond between oxygen and hydrogen?
Broke the bonds and split.
Broke the bond how?
Heterolytically.
Heterolytic, so the hydrogen took electrons away from
Oxygen.
oxygen. Does that make physical sense?
No.
Why not?
Oxygen's too electronegative.
Oxygen is way more electronegative than our hydrogen. That does not make any physical sense for that hydrogen to take the electrons from our oxygen. So it comes back to organic chemistry and looking at that balance of electronegativity. Okay? Not a bad idea to attempt it, but then evaluate what that means. What that meant was that that oxygen had to lose electrons to a lowly hydrogen atom. That doesn't make any sense. Okay? So let's try the other option, the other hydrogen that potentially changed. Okay? What would it have to do?
Take those electrons from carbon.
Take the electrons from carbon. Carbon is more electronegative than hydrogen, though.
Yeah,
By how much?
not much.
Not much at all. They're almost identical in electronegativity. Okay, so that hydride isn't just going to pop and come flying off on the carbon. Something has to help that hydride leave.
Resonance?
What pi bond? This oxygen can share its electrons with that carbon. Now the carbon has too many electrons, which can now pop off the hydride that can then hook up with our NAD+. The result, how an organic chemist would at least look at this, would be this structure. I don't feel like drawing in all the electrons like they did. Okay. What's the problem with this structure? The oxygen is now positively charged. Does oxygen want to be positive? No, so what happens? It steals the electrons from hydrogen, which puts us at our final state. Okay. That's how an organic chemist would kind of look at this reaction, facilitating each of those transfers. Okay. What does a biochemist do with the arrows?
So what happens to that hydrogen then? It just goes,
It floats off into
it
solution.
has no electrons.
It has no electrons. It comes off as H+, which means what happens to the pH?
Our buffer system kicks in.
Okay, our pH would reduce, our buffer system kicks in to level out that pH imbalance. Okay? So what does a biochemist go through and do? Instead of showing the electrons from the oxygen, which are the closest ones to shift in, we show the electrons from the oxygen-hydrogen bond immediately shuttling in. Okay? If we wanted to get even fancier with this, there's probably an enzyme floating around with a negative oxygen that can pick up the hydrogen. Okay? So it's stringing the reactions together in a way that facilitates that reaction to occur. Okay? So NAD+ facilitates all these reactions in a 2-electron transfer process. Yes?
Shouldn't it be, for the product side, 1 H+ and 1 hydride
So
plus 2
this
electrons?
is something that bothers me with how biochemists are representing this. Okay? The electrons cannot be sent off on their own. And that is what this is showing. Okay?
So
They're trying to show it out in a reduction-oxidation half reaction. And in the half reaction, you're transferring the 2 electrons out, and we're saying those aren't associated with the hydrogen.
Okay.
Depending on what you're looking at and how you want to look at it, you're going to see a slight variation of that. Okay? So they're trying to accent the fact that that was a loss of electrons, oxidation in the first step. Okay? As opposed to saying, looking at, say, maybe the increase in oxygen bonds as making it the oxidation.
Okay.
Okay? Other questions on that? Fun stuff. Okay. Another structure that's often used, very similarly to NADH, is either FMN or FAD. If you're looking at Flavin dinucleotide or Flavin mononucleotide. Took me a little while to process this, but if we take a look at this reaction, your FMN, oh shoot, we didn't talk about nucleotides. Anybody remember what a nucleotide is?
Amino acid sequence?
No, the other one. Part of DNA. Nucleotides are your DNA molecules.
Yeah, the 5-pentose
Okay.
sugar, a
It's
phosphate group, and
A nitrogenous base, okay, in this case that's adenosine, attached to a sugar molecule. Okay, that is a nucleotide. Okay, so why might I have a slight issue with this? So flavin adenine dinucleotide, cool, I see the dinucleotide, or I see the nucleotide, but it says di. What does di mean? 2. Well, maybe they're just making stuff up. What's an FMN? FMN is crap. Mononucleotide. But the FMN is just this upper portion. Where's the other nucleotide? What's that?
The bottom loop.
That's the dinucleotide. Where's the second nucleotide? So that's one nucleotide for sure. Okay, and this is going to be the one in FAD with our dinucleotide. Where's the other nucleotide? There's your other nucleotide. Okay. We still have a nitrogenous base. We still have a sugar molecule, our carbohydrate. Okay. Yes, it does not look the same. It's a derivative of it. Okay. That's fine. It's just, but it is there. Okay. The that nucleotide, as best I could see, was, oh crap, I wrote it in my notes. It was uracil, I think. I didn't write it in my notes. I believe it looks like uracil if you wanted to really get into it. Okay. So this is our FAD molecule. Where do we expect the chemistry to occur? Remember, it's similar to NADH. And NADH, what happened with our chemistry? Where was it occurring?
Nitrogen.
Up at our nitrogen. So we need to find a nitrogen where our chemistry can occur. There's a bunch of nitrogen. Oh, come back here. Now I'm cheating. You saw that. There's a bunch of nitrogens down here in the nucleobase. Okay. But if we go all the way back to NADH, what was the NAD? Nicotinamide adenosine. Okay. So NADH also has this same AMP molecule at the bottom. Okay. Our reaction chemistry is happening all up here. Okay. That's where we're getting our shifting around of our electrons and ultimately our hydrogens. Okay. So it does pretty much the same thing as our NAD. What makes it slightly different is not only does it accept electrons in the form of hydride, but it also accepts a proton. What we end up transferring between, whoa, my screen just went weird, is we end up going from FAD to FADH2. But the charge didn't change. Why is this still doing the same thing as NAD plus to NADH?
Adding 2 hydrogens.
It's not just adding 2 hydrogens, but it's the right idea. If they were 2 protons, what happens to the charge?
Plus, it gets less negative.
It would get less negative. Did it change? No, it stayed exactly the same. So it's not just adding 2 protons. It's adding a proton with a positive and a hydride with the negative. That's why we have 2 hydrogens on there. Okay. So this is still doing ultimately the same thing, but it's also accepting a proton in that same process, which then hides your charge change. Okay. Because ultimately the charge doesn't change in the course of that reaction. So how does it go through and do this? Okay. Again, they're trying to show the balance of electrons as you shift through. Okay. We can take our hydride as our H minus, and we've got 2 possible locations for it. But we could swing it in here. That nitrogen then has too many electrons, so what has to happen? If it has too many electrons, what do? We have to break a bond, so we'll break a pi bond, and we can rotate it up to there. But then how many electrons does our carbon have? Too many bonds, so what happens? We break another pi bond, and it kicks those electrons up onto the nitrogen. Okay. The net result of this is what happens.
2 hydrogens are pretty tough.
Careful, I haven't put in a second hydrogen yet, have I?
No, but you have that lone pair that's on that nitrogen that strips the
What charge is that nitrogen now?
negative
It's formally negative, which now makes it a really good
base.
base. It can pick up an H plus from our solution to do our final transfer across. Okay. The trickier thing with our FAD molecule and its interchange is that because it is a much larger structure, let's see, do I have a better picture? Shoot, I don't have a better picture. This will have to do. If we take a look up at the active site, okay, It is a much larger structure, and it is much more conjugated with pi bonds. That conjugation of pi bonds allows for the stabilization of reactive intermediates, like the negative charge, okay, but also like a radical. So one of the problems with our FAD molecule is not only can we do this 2-electron shuttling, like our NADH or our NAD, okay, but it can shuttle 1 electron at a time. With a single electron motion, we now have a radical species, which does some more interesting chemistry for us, but it can also generate potentially all sorts of other dangerous side products, like free radicals floating through our environment. Okay? So FAD is great for this transferring process. Kind of depends on what we're trying to look for and what we're trying to work with. Okay? So we'll see it pop up in similar roles to our NADH, and depending on what molecules we're looking at or what we're trying to do, we'll end up using one over the other. What's that preference going to come down to? Probably the evolution of the enzyme, okay, that used either of these molecules. They have drastically different structures overall. You've got a much larger structure with the FAD than you do with the NAD. Okay, so you're going to see different interactions on where they can get to. The last one, which I don't agree with how the textbook organized it, but it's here anyway, is using ATP, our standard molecule. So we've got our structure of ATP. Yep, sorry.
That slide just, can you go back one
Yep.
second? Okay. When we were talking about FAD to FAD,
H2.
you said it wasn't reduced because,
I didn't say that. It is reduced.
okay, kind of,
Yeah. No, we transfer H plus and we transfer 2 electrons into it. So if we just brought H plus into it, it's not a reduction reaction. If we bring in H minus, as soon as we have 2 electrons, it's a reduction. Okay, so it did absolutely gain 2 electrons. It's a question of how does it do it. Does it do it in pairs or does it do it individually? And it can do it either way. ATP to ADP, all we're looking at doing is cleaving this group off. Okay, and we were replacing it with an O minus. Okay, with that O minus comes from water. What do you think? Oxidation, reduction?
reduction.
Or trick question?
For it to be reduction has to be oxidation, is that right?
True, but we've been looking at half reactions as we shift through. Okay, so we could just envision this as half reactions.
Reduction?
Okay. What happened to this phosphate, or this phosphorus?
Isn't that whole entire compound stripped off?
This whole piece
Yeah.
disappears and comes loose. What happened to the number of oxygen bonds to this phosphorus? If this whole piece comes off,
It stays the same.
stays the same. So it was not oxidized or reduced. What happened to this phosphorus? It lost an oxygen and
Gained it back.
gained it back, which means
Nothing happened.
nothing happened to it. What happened to the rest of the structure?
Nothing.
Nothing. Oxidation or reduction?
Nothing.
Neither. Okay? So ATP is not an oxidation or reduction reaction. What we're doing is transferring a high energy phosphate bond back and forth. Okay? That high energy bond is allowing us to do a lot of the electron transfers. So what then comes out of this is, why is that a high energy bond? Okay? Well, what happens, to erase all of that, when I bring a negative near a negative? It repels. Now that I've got this bond in there, it can't repel. What does it want to do? Break off as quickly as it can. Right? So the transfer of that phosphate across releases a bunch of energy because we're releasing that tension of that negative-negative repulsion. Okay? We can translate that even further out into not just looking at the negatives, but looking at all of the oxygens around each of those as well. Okay? So it's that kind of electrostatic repulsion that gives us the biggest source of energy. The other thing that we could go through and evaluate would be a change in entropy, which I know everybody loves entropy, so we'll just kind of leave that one alone. You can go through and take a look at the textbook when they talk about it, but that's also involved in this. Okay, the biggest one is that electrostatic repulsion. How does that help us out further on down the road with other reactions? Well, I'm now transferring something with a big electrostatic negative charge to another molecule, which could potentially have electrostatic negative charges. Okay, we're going to end up transferring that repulsive effect through our molecules down the chain. So we end up transferring that energy across at each stage. What happens ultimately is we end up losing a little bit of that energy. Okay? We don't get thermodynamic perfect systems. Okay? So we can use that energy release to facilitate another reaction happening. And this is where we get coupling happening within this. So instead of looking at our oxidation and reduction reactions with transfers of electrons, we can look at it as a transfer of energy. Whoops, there should be a plus there. Okay. So as I go from ATP to ADP, that release of energy can then be consumed by something else, okay, and can facilitate that reaction occurring. Okay, which brings us to an example reaction. If we take a look at glucose to glucose 6-phosphate, this reaction has, come back here. Don't look at that. That's not relevant actually for answering that. A delta G, where is it? Positive 14. I don't really care about the units. I think it's kcals per mole. Is this reaction one that's likely to occur on its own? Why is it not likely to occur on its own? It's a positive delta G. This reaction is endothermic. We're going up in energy. Those reactions are not feasible. Okay? This is the first step in glycolysis. Kind of an important step to occur. If it's not going to occur, we don't get glycolysis. Okay? So what happens? Well, we could look at ADP and ATP. Okay? Well, what happens when we look at ADP to ATP? Well, the delta G in that case, where's my number? Plus 31. Same deal, same units. Uh-oh. Does that mean this reaction works? No. Huh. So how does this work? What changes as we go from glucose to glucose 6-phosphate?
You added a phosphate.
We add a phosphate. What changes when we go from ADP to ATP?
You dephosphorylate.
We added a phosphate. Both of these are doing the same thing, adding phosphates. What should we do if I actually want this to work, where we transfer one to the other? Do the reverse reaction. Instead of doing ADP to ATP, let's do ATP to ADP. What happens to the delta G? Now it goes negative 31 kcals. I no longer need to worry about that, come on, that middle one. And now when I run the reaction, what happens? When I couple these two simultaneously, what's the net result for the delta G? Negative, I don't care what the number is, but it's negative. Okay. What does that negative mean? Now the reaction is spontaneous and can occur. We've supplied the energy to transfer that across. ATP does a good job of doing this. Okay? So we're facilitating that electron transfer process. Why would this first one be non-favorable? Remember, we're putting on a highly charged species, which is going to repel away. Okay? We definitely got to end there.